So this is my video on hyperbolic functions. Hyperbolic functions are kind of like analogies to trig functions that we already know. So let's define them. So the first definition is what is known as hyperbolic sine x, and that is defined as e to the x minus a to the negative x over 2. And that one is cosh, which is hyperbolic cosine x, which is defined as e to the x plus e to the, should be plus here, negative x over 2, and tangent, hyperbolic tangent or tan x is defined as e to the x minus e to the minus x, so e to the x plus e to the minus x. And just like in what we know, it is the sine, hyperbolic sine over the hyperbolic cosine. So once again, hyperbolic sine is defined as e to the x minus e to the negative x over 2. Hyperbolic cosine is defined as e to the x plus e to the negative x over 2. Hyperbolic tangent is divided as the quotient of these two, which is e to the x minus e to the negative x over e to the x plus e to the. Let's take a curve and let's look at the graph. So the red graph is the graph of the hyperbolic sine, and you can kind of see that these two graphs, which is e to the x divided e to the negative x over 2, this is decay, so negative of e to the negative x over 2. So this part, negative of negative, just the this part, okay, the right hand, e to negative of negative e to the x over 2. And if you look at the blue curve, that would be e to the x over 2. So this will be negative e to the negative x over 2. This will be e to the x over 2, and really the shin is the sum of these two. So e to the x over 2 plus negative of e to the negative x over 2. You can see that how these two curves actually sum together, right? And if, for example, if you're at that point, the values of the curve cancel each other and you get 0, making hyperbolic sine 0 equals 0, okay, and so on. So this red graph is hyperbolic curve. So if we look at the hyperbolic cosine, right, again we have the red graph, which is the sum of e to the x over 2, which is the blue graph, and e to the negative x over 2, which is the green graph. And if we see a kind of a shape like a necklace type of thing, and this is called a catenary in engineering and physics. So kind of like a catenary shape, right? And the formal equation of a catenary is this, which involves c plus a times hyperbolic cosine of x over a. And again, you see that shape that you saw here. And this is used in engineering as, for example, if you take two telephone or two towers, if you put a wire between them and let it fall free under gravity, the wire will shake the tape of a catenary. Another example of a catenary comes up if you look at the St. Louis gateway arc. You will notice that the shape is not really a parabola; it is actually a catenary. A necklace usually on the neck usually takes the place of a catenary, and so on. It's a pretty important application in engineering and physics. Okay, so let's look at some results. First of all, hyperbolic cosine squared minus hyperbolic sine squared equals 1. So this is like the Pythagorean trick, but except with the Pythagorean we have cosine x, cosine squared plus sine squared equals 1. This is hyperbolic cosine squared minus hyperbolic sine squared equals 1. So how do you show that? Well, let's take the left hand side with hyperbolic cosine squared minus hyperbolic sine squared. So hyperbolic cosine x is e to the x plus e to the negative x over 2. So if you square that, you get e to the x plus e to the negative x squared over the 2 becomes 4 plus minus, actually this should be minus hyperbolic sine is e to the x minus e to the negative x quantity squared, okay, and that is the sine squared, and then again there's a 2 on the bottom, and this 2 on the bottom, right, okay, and that will become 4, okay. So this squared, right, e to the 2x, e to the x minus e to the negative x squared over 4. So when you simplify that, you will see that if you take a 1/4 outside from here, and if you distribute, so 1/4 outside, and if you distribute this square, you get, watch me carefully, e to the 2x, e to the 2x. Now what about the middle term? You have twice e to the x, e to the negative x. Now e to the negative x and e to the x will multiply to give, when you multiply, remember you add the, when you multiply you add the indices, so exponents, so x plus negative x is 0. So you get e to the 0, which is 1. Or in other words, you can say that when they multiply, they will cancel each other because this is e to the x and this is 1 over e to the x. So they will cancel each other and give you 1, and there's a 2. It's because it's twice the product of the two terms. So it's 2. And the last term is the square of e to the negative x, which is e to the negative 2x. And from that you subtract. Once again, you square this one, you get e to the 2x, right? And then you multiply the middle, the two terms here, they will cancel off, giving a 1 and times 2 because we need to multiply by 2. So negative 2 plus e to the negative x squared, which is equal to e to the negative 2x, right? And then what will happen is we will see that e to the 2x and e to the negative 2x will cancel off. 2 plus 2 is equal to 4. And e to the negative 2x is once again with negative e to the negative 2x, it will cancel off. So this should be negative. The cancel off, and all you will have is a 2 plus 2, okay, which is 4. So you have 1/4 in front, so 1/4 times 4 is, and that's equal to 1. So this is a beautiful result. It's the analysis of a Pythagorean for hyperbolic. Cosh squared minus shin squared equals 0. So sometimes it is easier to say that without saying hyperbolic cosine and hyperbolic sine, and we say cosh and shin, right? I will try to stick to that, not a kind of word, right? And then likewise, we can define not just cosine and sine, but you can define tan, right? And then you have the inverse sines of those, right? So here are some results, right? Okay, so there are like the shin of negative x is negative shin x, cosine cosh of negative x is cosh x, and then we already proved that, and we can easily prove this one. And then just like you have a sum formula for sine and cosine, you have a sum formula for shin and cosh. So let's take one of them and prove. So if you want to prove this one, right, as identity, right, that is 1 minus tan squared x is equal to sec hyperbolic secant squared x, right? Okay. And so how do you do that? We start with the Pythagorean type identity, which is cos squared minus sine squared equals 1, and then you divide both sides by cos squared. So when you divide this by cos squared, this goes off and you get 1 minus your shin squared over cos squared, which is tan squared. And when you divide, and that's the left side, and then you go to the right side and you divide 1 by cosine squared x. So but 1 over cosine squared x is equal to the hyperbolic secant squared x. So really in the end you get the equation 1 minus tan squared is nothing but hyperbolic secant squared. Once again, this is kind of analogous to the result that we have in trigonometry, that 1 plus tangent squared is equal to secant squared x. Okay. So now let's look at the derivatives of these functions, right? So suppose you want to find the derivative of shin x, right? So you want to find the derivative of this, right? That means the shin x is this. So find the derivative of this. Okay, 1/2 times, so 1/2 is a constant. You can take it out, and you want to find the derivative of e to the x and e to the minus e to the negative x. So let's try that, right? Okay. And then when you actually, this is pretty easy because the derivative of e to the x is itself, and when you take the negative of e to the negative, the derivative, it's e to the negative x, but the negative comes times negative 1 by chain rule, and then that negative and this become negative becomes positive, so you will get e to the x plus e to the negative x over 2. Okay, so this becomes a plus, right? But e to the x plus e to the negative x over 2 is nothing but the cosh. So just like in trigonometry, we have the derivative of shin is equal to the cosh. So unlike in trigonometry, the derivative of cosh also can be shown to be equal to shin, and then the derivative of tan again is inverse secant squared x, something again very analogous to trig, and then you can see the other derivatives also being very analogous except for different minus signs and stuff like that. So let's do an example. Suppose you want to differentiate a shin of x squared. Well, just use chain rule. You use the so when you see from outside, you only see the shin. You see some shin of some junk. So to differentiate that, you get cosh of that junk. So that is cosh x squared. But then you go inside and you see x squared. Later the derivative and multiply, you get 2x, right? And now let's take another one. You want to differentiate tan of x squared plus 1. Well, out from outside you see tan of some junk. So when you differentiate that, you get inverse hyperbolic secant squared, right, times the junk. And then you want to differentiate the junk, you get 2x and you multiply by 2x. Okay. So now let's do an integral. So you want to integrate this one, x times cosh x squared dx. Well, you can already see that you can put a u substitution here. But u cos x squared, the derivative is 2x, which you take off the leftover terms, right? So you put u cos x squared, and then du is equal to 2x. So when you do that, you get a half coming from, when you solve for dx, you get a half. That is that half, and then integral, the x get cancelled off with the derivative of this. The 2x comes from the derivative. So x is gone. You get cosh of u, which is x squared. Really the integral of cosh of u, but we know that the derivative of shin is cosh, so the integral of cosh is sin. So we have 1/2 times shin of u, but we know that u is equal to x squared, so it's 1/2 times x squared. Okay. Now in the same spirit, let's talk about hyperbolic functions. Now we know that inverse hyperbolic functions. Now we know that there are inverse sine functions, and so if for example, if y is equal to sine inverse sine of x, then sine of y is equal to x. So similarly, if you take y equals inverse shin of x, then shin of y is equal to x, and you can similarly define cosh inverse of x and tan inverse. So if you just take the shin and put it under y, you should get back x. That's the idea. Okay. So this is a very beautiful result. Actually, the inverse shin of x is equal to natural log. So it's a result which connects the inverse shin with the natural log, which is not all that strange because the shin involves exponentials, and sometimes exponentials, the inverse is the natural log. So you would expect something like this to come. So let's try to prove that. Okay, so one way of proving that would be, if you want to prove that the inverse shin of x is equal to natural log of this, then it's the same as if you can show that the shin of the natural log, okay, the natural log of this is actually equal to x, the same that. Okay, so to be careful, let's put a little parenthesis here to show that we are taking the quantity of the natural log. Okay. So now by the definition of the shin, so what is this then? It's e to this junk minus, go back to the definition, right? E to the x minus e to the negative x over 2. Okay, alright, so is e to, so let's kind of put that in, right? Okay, so if you take that, right, and so if you put that and compare this with that, is e to the whatever the argument. So the argument here is natural log of this junk. So e to the natural log of this junk minus e to the negative of that full argument, the e to the negative natural log of that junk. But we know that the e and the natural log cancels off. So you will get straight away x plus x squared, square root x squared plus 1 here, because the e and the natural log of cancel off. Here you have to be careful because the e and the natural log will immediately not cancel off, because you will have to get rid of this minus 1 first. So what you do is you take it as a power. So if you then this becomes e to the negative, instead of this you get e to the natural log of this chunk to the power negative 1. And now you can cancel off the e to the natural log, but you will get, the answer will be this to the power -1, or in other words 1 over this. So again, because you can't simply cancel off the e to the negative ln, you need to take the negative as a power of -1, which makes it go under, and then you can cancel off e to the e and the negative log of n. So it comes to this, and now you take the common denominator, right, and x plus x squared plus 1, and you multiply both sides of that. So you'll be really squaring x plus x squared plus 1 times x squared plus 1, and that will give you this, and then there is a -1 here, -1, and then you have a common denominator x plus square root x squared plus 1. So now the 1 and the 1 will cancel off, you can see that, right? And then you will actually have a 2x, right? So you will also have a 2x squared, right, and x squared, and so in the end you will get this will cancel off, so you will actually have 2x times x times square root x squared plus 1 over x times x squared plus 1. So this will cancel off, and the 2 will cancel off, and you will just have x at the end. Okay, so then I need to put another x squared here, because when you square the second term, you get another x squared, I think, right? So here, and minus subtract 1, and now the x squared and the x squared, which becomes 2x squared, right? And then if you so you have, then you take out an x from that and a 2 from that, and you get 2x, right? So you get a 2x squared, right, plus 2 of this junk. You get a 2 and an x from that, and you're left with x plus x squared plus 1 square root, and that will cancel off with x plus x squared root. 1 square root will cancel off because 1/2 times 2x is equal to 2x. So we proved that the shin of the natural log of this is nothing but x. Okay, and so which means that the inverse shin of x is the natural log of this. All right, so we can do an integral, right, from 0 to, so what this also says is that so another result, right? Okay, if y is equal to inverse shin of x, and the dy over dx is this. Well, now that we know, then it's the same as, so we know that the inverse shin of x is the same as natural log of x plus square root x squared plus 1. So when you mean the derivative of the inverse shin inverse x is the same as taking the derivative of the natural log of x plus x squared, because from the previous result we did show that the inverse shin of x is natural log of. So it's a matter of differentiating this now. So to differentiate that, you go 1 over the junk. So you have 1 over the junk, and then you go inside the junk and you simplify, which you get 1. The derivative of x is 1, and then we differentiate the derivative of this, right? You use chain rule. You get 1 over twice the radical times the derivative of what is inside is 2x. So 2x times twice the radical. So once again, if you do the denominator and you simplify, you will land with final answer is this. So the derivative of inverse shin is this, which is a beautiful result in a way, because that also shows that the antiderivative, or the integral, indefinite integral of 1 over x squared plus 1 is nothing but shin, because the derivative of this is this, then the integral of this is inverse shin of x. Okay, I'll do a final example with that. Okay, and that's it for this video. Thank you for watching.